Welcome to this comprehensive scientific lecture on a critical question facing modern research. Can artificial intelligence be used to interpret research data, develop physical and chemical models, and is this approach ethical? This is a question that touches the very foundation of scientific methodology. We stand at a crossroads in scientific methodology. On one side, we have traditional science built on centuries of human interpretation and hypothesis testing. On the other, we have emerging AI-driven approaches that promise unprecedented pattern recognition and modeling capabilities. Let's begin by examining the traditional scientific method that has guided research for centuries. Understanding this foundation is crucial before we can evaluate AI's role. The scientific method follows a structured pathway. We begin with careful observation of natural phenomena. From these observations, we formulate hypotheses based on existing theoretical frameworks. We then design experiments to test these hypotheses and finally analyze the results to draw conclusions. Throughout this entire process, human intuition, creativity, and domain expertise guide every decision. Scientists draw upon years of training and accumulated knowledge to interpret what they observe. In traditional research, experiments generate data points. Each measurement represents hours of careful laboratory work. Scientists then examine this data, looking for patterns, anomalies, and relationships that might reveal underlying physical or chemical principles. However, there's an inherent limitation. Human cognition can only process and visualize data in limited dimensions. When dealing with complex systems involving dozens or hundreds of variables, our ability to detect subtle patterns becomes severely constrained. This brings us to artificial intelligence. AI systems, particularly machine learning algorithms, offer capabilities that transcend human limitations in specific domains. Let's examine what AI can actually do. AI systems, particularly deep neural networks, can process vast amounts of data simultaneously. They can identify complex, non-linear patterns in high-dimensional spaces that would be invisible to human analysis. This capability has revolutionized fields, from particle physics to genomics. AI excels at finding correlations in datasets with hundreds or thousands of variables. It can detect subtle relationships that emerge only when examining the full complexity of the system. I can fit extraordinarily complex mathematical models to experimental data, often achieving predictive accuracy that surpasses traditional statistical methods. This has proven invaluable in fields like protein folding prediction. Consider this visualization of a multidimensional dataset projected into two dimensions. Traditional analysis might struggle to identify the boundary separating two classes of data. An AI algorithm can learn this complex decision boundary with high precision. Let's examine a concrete case study. In pharmaceutical research, AI has been used to predict molecular properties and identify potential drug candidates. This represents one of the most successful applications of AI in scientific modeling. AI systems can analyze millions of molecular structures, predicting their binding affinity to target proteins, their toxicity profiles, and their pharmacokinetic properties. This has accelerated drug discovery timelines from years to months in some cases. The most celebrated example is AlphaFold, which solved the decades-old protein folding problem. This AI system can predict three-dimensional protein structures from amino acid sequences with accuracy rivaling experimental methods. This represents a genuine scientific breakthrough enabled by AI. However, this success raises profound ethical and epistemological questions. Can we truly understand phenomena if the model is a black box? Is prediction sufficient, or must we demand mechanistic understanding? The fundamental problem is interpretability. Many AI models, especially deep neural networks, function as black boxes. Data goes in, predictions come out, but the internal logic remains opaque. Can we call this scientific understanding? The first major ethical concern is the potential loss of mechanistic understanding. Traditional science seeks to explain why phenomena occur, not merely to predict them. If we rely on AI models we cannot interpret, do we sacrifice the explanatory power that defines scientific knowledge? Compare Newton's second law with a modern neural network. The equation F equals ma is elegant, interpretable, and provides deep insight into the nature of force and motion. A neural network might predict trajectories with high accuracy, but it offers no such conceptual clarity. The second concern involves reproducibility. AI models can be sensitive to training data, hyperparameters, and even random initialization. Different researchers training similar models on the same data might obtain different results. This challenges the scientific principle of reproducibility. When different research groups train AI models on identical datasets, they may obtain different performance metrics and predictions. This variability raises questions about the reliability and generalizability of AI-derived scientific conclusions. The third ethical concern is data bias and overfitting. AI models learn patterns from training data. If that data contains systematic biases or represents a limited sample of possible conditions, the model will inherit and potentially amplify these limitations. Notice this dataset has a gap in the middle region. An AI model trained on this data might extrapolate poorly in that region, making unreliable predictions. In scientific research, we often must extrapolate beyond our training data, making this a serious concern. Having outlined the concerns, let's examine the counterarguments. Many researchers argue that AI represents a legitimate and necessary evolution of scientific methodology, not a departure from it. The first argument is pragmatic. Modern scientific problems often involve systems of such complexity that traditional analytical methods are simply insufficient. Climate modeling, genomics, and quantum many-body physics all generate datasets that exceed human analytical capacity. Compare a simple three-body system with a complex many-body system. The simple system might be solved analytically, but as the number of interacting components grows, traditional methods become intractable. AI offers a path forward for these complex systems. The second argument is that AI can serve as a hypothesis-generating tool. By identifying unexpected patterns in data, AI systems can direct human researchers toward novel phenomena worthy of deeper investigation. This represents a collaborative model where AI augments rather than replaces human insight. When AI systems identify anomalous data points or unexpected correlations, they can alert researchers to phenomena that merit further study. This anomaly detection capability has led to discoveries of new particle physics events and novel drug mechanisms. The third argument challenges the primacy of mechanistic understanding. Some philosophers of science argue that accurate prediction itself has scientific value, even without complete mechanistic explanation. If an AI model can predict outcomes reliably, it provides actionable knowledge. In medical diagnostics, an AI system that accurately predicts disease progression can save lives, even if we don't fully understand its internal reasoning. This utilitarian perspective suggests that predictive power alone justifies AI's use in research. Given these competing considerations, how should the scientific community proceed? Several ethical guidelines have been proposed to govern AI use in research. Let's examine these frameworks. The first guideline emphasizes transparency. Researchers must thoroughly document their AI methodologies, including model architectures, training procedures, hyperparameters, and validation strategies. This enables other scientists to assess and potentially replicate the work. Comprehensive documentation serves multiple purposes. It enables reproducibility, allows critical evaluation of methods, facilitates meta-analyses, and builds community trust in AI-derived results. This is essential for maintaining scientific rigor. The second guideline requires validation on independent datasets. AI models must be tested on data not used during training, preferably collected by different research groups or under different experimental conditions. This guards against overfitting and confirms generalizability. This validation pipeline is critical. The model is trained on one dataset, validated on a held-out portion, and then critically tested on completely independent data, ideally from different sources. Only if the model performs well across all stages can we have confidence in its scientific utility. The third guideline encourages efforts to interpret AI models mechanistically. Even when models are complex, techniques like attention visualization, sensitivity analysis, and feature importance ranking can provide partial insights into how models make decisions. By applying interpretability techniques, we can transform opaque black boxes into more transparent systems. While we may not achieve complete understanding, partial mechanistic insights are valuable and align AI use with traditional scientific values of explanation. The fourth guideline advocates for human-in-the-loop workflows. Rather than fully automating scientific discovery, AI should augment human expertise. Scientists should review AI predictions, validate unexpected findings experimentally, and maintain ultimate decision-making authority. This collaborative model preserves the essential role of human judgment while leveraging AI's computational power. The AI generates hypotheses or predictions, humans evaluate their plausibility and design validation experiments, and the cycle repeats iteratively. The ethical considerations vary across scientific domains. Let's examine how different fields face unique challenges and opportunities with AI integration. In physics, there's tension between theoretical elegance and empirical prediction. Physics has traditionally valued simple, elegant theories like general relativity. AI models with millions of parameters seem antithetical to this aesthetic. Yet in complex systems, like turbulence or quantum chromodynamics, AI may be necessary. This contrast illustrates the challenge. Do we accept AI models that lack theoretical elegance if they provide superior predictions? Or do we insist on interpretable theories even if they sacrifice some accuracy? Different physicists answer differently. In chemistry, AI has proven exceptionally valuable for molecular design. AI can predict reaction outcomes, suggest synthetic routes, and design molecules with desired properties. The ethical concern here is whether AI-designed molecules can be synthesized safely and whether researchers understand potential hazards. When AI proposes a novel molecular structure never before synthesized, we face uncertainty about its properties. Could it be toxic, explosive, environmentally persistent? Human chemists must carefully evaluate AI proposals before synthesis, maintaining responsibility for safety. In biology, AI tackles problems of immense complexity. Genomic data involves interactions between thousands of genes. Protein networks involve countless regulatory relationships. AI excels here, but the concern is whether predictions translate to actual biological organisms, with all their contextual complexity. This network represents gene interactions. In reality, thousands of genes interact in context-dependent ways. I can model these interactions computationally, but validating predictions in living organisms remains essential. Computer models cannot fully capture biological reality. This brings us to a fundamental philosophical question. What constitutes scientific understanding? Can we claim to understand a phenomenon if our best model is an inscrutable AI system? The traditional scientific view holds that understanding requires the ability to explain phenomena in terms of underlying mechanisms and causal relationships. This explanatory power is what distinguishes science from mere prediction or correlation. Consider this example. We observe the sun rising every day. But understanding requires explaining why this occurs in terms of Earth's rotation and orbital mechanics. Mere prediction that the sun will rise tomorrow, while useful, doesn't constitute understanding. However, pragmatist philosophers argue that if we can accurately predict phenomena and intervene effectively, we possess a form of understanding. The criterion is practical success, not metaphysical insight into essences. A compromise position recognizes multiple levels of understanding. I might provide what we could call operational understanding, the ability to predict and intervene effectively. Traditional mechanistic models provide deeper causal understanding. Both have value in different contexts. This hierarchy shows different levels of scientific understanding, from deep causal insight at the top to pure predictive capability at the bottom. AI-based models typically operate at the lower levels, but they can guide us toward deeper understanding by revealing phenomena that warrant mechanistic investigation. Let's examine a concrete case where these issues play out: climate science. Climate models are among the most complex in all of science, and AI is increasingly used to improve predictions and analyze data. Climate science must model interactions between atmosphere, oceans, land surface, ice sheets, and biosphere. Each component has complex internal dynamics, and they're all coupled. Traditional physics-based models struggle with some of these interactions, particularly clouds and precipitation. AI is used to parameterize subgrid processes, phenomena that occur at scales smaller than the model's resolution. For example, cloud formation happens at scales of meters, but climate models have grid cells hundreds of kilometers across. I can learn relationships between large-scale conditions and subgrid cloud behavior. This raises an ethical question. Climate models inform trillion-dollar policy decisions about emissions reduction and adaptation. If parts of these models are AI black boxes, can we trust their predictions? What if the AI learns spurious correlations that fail under future conditions? We face a trade-off. Pure physics-based models are transparent and grounded in established theory, but they may miss important processes. AI-enhanced models may predict better, but with less mechanistic clarity. Climate scientists must balance these competing demands. Peer review must evolve to handle AI-driven research. Traditional peer review assesses whether methods are sound and conclusions justified. But how do reviewers evaluate a neural network with millions of parameters? The first challenge is reproduction. Reviewers typically cannot retrain complex AI models from scratch. They must rely on author documentation and release code. This requires new standards for code and data sharing in scientific publishing. AI-driven research requires supplementary materials beyond traditional papers. Reviewers need access to code, data, trained model weights, and comprehensive documentation of training procedures. This expands what constitutes a complete scientific publication. The second challenge is evaluating model choices. Why did authors choose this architecture rather than alternatives? How sensitive are results to hyperparameters? Reviewers must assess whether modeling choices are justified and whether sensitivity analyses are adequate. The third challenge is assessing generalizability. Has the model been tested on sufficiently diverse data? Are there conditions under which it might fail catastrophically? Reviewers must evaluate whether authors have adequately probed their model's limitations. The integration of AI into scientific research has profound implications for how we train the next generation of scientists. What skills must future researchers possess? Future scientists need hybrid expertise, spanning domain knowledge, statistical thinking, and computational skills. A physicist must understand both quantum mechanics and machine learning. A chemist must know both organic synthesis and neural network architectures. The intersection of domain expertise and AI skills creates the future scientist. Neither alone is sufficient. Domain expertise without computational skills limits research scope. AI skills without domain knowledge leads to models that violate physical principles or miss important phenomena. Science curricula must integrate computational thinking from the beginning. Students should learn programming and data analysis alongside traditional coursework in physics, chemistry, and biology. The artificial separation between computational and experimental science must dissolve. AI-driven research raises questions about funding and resource allocation. Should funding agencies prioritize AI-based approaches? How do we balance investment in traditional experimental science versus computational modeling? There's risk of funding concentration. AI research often requires expensive computational resources and large datasets. This could advantage wealthy institutions and disadvantage smaller labs, exacerbating inequalities in scientific research capacity. This disparity threatens scientific equity. If AI becomes essential for competitive research, labs without computational resources face disadvantage. Funding agencies must consider how to democratize access to AI tools and computational infrastructure. Potential solutions include shared computational resources, cloud computing credits for researchers, and open-source pre-trained models that smaller labs can adapt. The scientific community must ensure AI doesn't create a two-tier research ecosystem. AI-generated discoveries raise novel intellectual property questions. If an AI system discovers a new material or drug candidate, who owns that discovery? The researchers who trained the model, the institution, the AI developers? Traditional intellectual property law assumes human inventors. Patent and copyright systems are built around human creativity and ingenuity. AI challenges these foundations. Can an AI be an inventor? Current legal systems say no, but the question remains contentious. When an AI discovers something novel, ownership becomes ambiguous. This uncertainty may slow commercialization of AI-driven discoveries and complicate academic industry partnerships. Clear legal frameworks are needed. Many argue for maximum openness. Scientific progress depends on sharing knowledge. If AI-generated discoveries are locked behind patents and proprietary models, progress slows. Open science principles suggest AI models and their outputs should be freely available. However, developing sophisticated AI systems requires massive investment. Companies and institutions need some IP protection to justify these investments. Pure openness might reduce incentives for developing advanced AI tools. Balancing openness and protection is challenging. We've explored numerous dimensions of this question. Let's now synthesize the competing arguments and work toward a balanced ethical framework for AI in scientific research. First, we should view AI as a tool that augments human capabilities, not a replacement for human scientists. Just as microscopes and telescopes extended our sensory capabilities, AI extends our analytical capabilities. The human scientist remains central. The scientist sits at the center, wielding multiple tools. The microscope reveals the small, the telescope the distant. The computer enables calculation, and AI enables pattern detection. Each tool expands capabilities without replacing human judgment and creativity. Second, we should recognize that appropriate use varies by domain. Medical diagnosis AI requires different standards than particle physics AI. Regulatory frameworks should be flexible and domain-specific rather than one-size-fits-all. Third, transparency is non-negotiable. Any scientific work using AI must thoroughly document methods, share code and data where possible, and clearly state limitations. The black box must be opened as much as technically feasible. Fourth, validation must extend beyond computational testing to real-world experimentation. AI predictions should be viewed as hypotheses requiring experimental confirmation, not as established facts. The empirical foundation of science must be preserved. This workflow must be standard. AI makes a prediction or identifies a pattern. This generates a hypothesis. Scientists then design experiments to test that hypothesis. Only confirmed predictions contribute to established scientific knowledge. Fifth, scientific education must evolve to produce researchers comfortable with both traditional methods and AI tools. Interdisciplinary training is essential. We need scientists who can code and coders who understand science. While AI has legitimate uses in research, we should establish ethical red lines, uses that should be prohibited or heavily restricted due to risks they pose to scientific integrity or public welfare. The first red line is fully automated hypothesis testing without human oversight. AI systems should not autonomously design experiments, collect data, and publish conclusions without human evaluation at every stage. This preserves human responsibility for scientific claims. This scenario should be prohibited. While each step might involve AI assistance, human scientists must evaluate hypotheses for plausibility, review experimental designs for safety and validity, and critically assess conclusions before publication. Complete automation removes accountability. The second red line is publishing AI-driven results without providing reproducibility materials. Papers using AI must include code, describe data sources, and document training procedures. Without these, the work is irreproducible and lacks scientific validity. In conclusion, I will undoubtedly continue to transform scientific research, offering unprecedented capabilities for pattern recognition, modeling, and prediction. As we integrate AI into our methodologies, it is crucial to address the ethical, epistemological, and practical challenges that arise. By acknowledging these challenges and developing guidelines that promote transparency, reproducibility, and human oversight, we can ensure that AI enhances the scientific enterprise without compromising its core values.